Hi there. This week we're going to be discussing differentiation. Differentiation is quite important in engineering because differentials can essentially represent how one parameter changes as we change another parameter. So for example, acceleration is the rate of change of velocity with respect to time. So that is the differential of velocity with respect to time. So first, let's look at standard differentiation. Okay, so let's say that we want to differentiate a standard polynomial function. So that's represented here as y is equal to a, so a is just some coefficient, some arbitrary number, multiplied by x to the power of n. Again, n is just some arbitrary number. The differential of that function is then equal to a multiplied by the original power n. So that n now comes down in front of the x as a multiplier. That's then multiplied by x, and the new power changes to n minus 1. Okay, so essentially we multiply the function by the original power and minus 1 from the original power. Okay, so let's look at an example. Here we have y is equal to 5 multiplied by x to the 4. So our differential of that, dy with respect to x, so dy by dx, is equal to 5 multiplied by the original power 4 multiplied by x to the power of 4 minus 1. So if we multiply the 5 and the 4, we have 20, and then we have x to the power of 3. Okay, so that's fairly straightforward. So where things can get a little bit more complicated is when the x function is on the bottom line of a fraction, so it's the denominator. And what we have to do is be able to sort of write the equation in this form here, so that we can then use the expression for dy by dx that we have in this blue box. So the first thing that we should do for this example here, where we have y is equal to 5 divided by x to the power of 4, is take the x to the power of 4 up to the top line, and we can do that by saying x to the power of minus 4. So we now have 5 multiplied by x to the power of minus 4. Hopefully you remember that from previous math study. We can now differentiate because we have it in the form that we need. So dy by dx, differential of y with respect to x, is now equal to 5 multiplied by minus 4 multiplied by x to the power of minus 4 minus 1. So if we multiply that out, we get minus 20 x to the minus 5. Okay. What we do want to do here is present our answers with a positive power of x. So essentially we have to take that x function back down to the bottom line. So the answer should be written as minus 20 divided by x to the power of 5. Okay, so that's the final answer for that example. So now let's look at what happens if you want to differentiate an exponential function. So here we have y is equal to e to the power of ax. So e is just the mathematical constant that we discussed previously when we looked at logs and exponentials. And again, a is some arbitrary constant, some coefficient of x. So if we want to differentiate this function, what happens is that the coefficient of x which is a, comes down in front as a multiplier, but in this case the power a to the x just stays exactly the same. It does not change. Okay, so I just want to point out that exponentials are the only place where the power doesn't change. Okay, so let's look at this example where we have y is equal to 4 multiplied by e to the power of 4x. If we want to differentiate that, then y by the x is equal to 4 multiplied by this a, which is 4, times by e to the 4x, because the power doesn't change. Okay, so that means that we can write 16, so 4 multiplied by 4 gives us 16 e to the 4x. And that's the final answer for that example. Okay, so let's now look at differentiating natural logs. So hopefully you remember from our previous studies of logs and exponentials that a natural log is a log with a base equal to e, the mathematical constant. So if we have a function y is equal to the natural log ln of ax, so again a is just some arbitrary constant, some coefficient of x, then y by the x is actually just equal to 1 over x, okay? So it doesn't actually matter what the value of a is here. It will essentially disappear in the differential. So let's take a look at an example. So if we have y is equal to 8 multiplied by the natural log of 5x, then y by the x is equal to 8, because that's just a constant, multiplied by the differential of the natural log of 5x, which is just 1 over x, okay? So the 5 is not part of the differential. So we can then just write that as 8 over x. And that's our final answer for that example. So what if we have a natural log of a function of x? So that function could be quadratic, it could be cubic, and essentially the differential of a natural log of a function of x is equal to the differential of the function, which is represented here as f dash x, divided by the original function itself. So to take a look at what I mean, let's look at this example. So we have y is equal to the natural log of 5x cubed plus 3x squared plus 2x. So our differential, y by the x, is equal to the differential of the thing inside this bracket divided by the thing that's in the bracket. So let's look at the differential of the thing inside the bracket first. We have 5 multiplied by 3 gives us 15, and we have x to the 3 minus 1 is 2. We have 3 times 2 gives us 6, and then the x squared just becomes x, and then 2x just becomes 2. And we can then divide through by 5x cubed plus 3x squared plus 2x. And that is our final answer for that problem. Now let's think about differentiating trig functions. So first we'll think about a sine function. So let's say that we have y equal to the sine of ax. Again, a is just some coefficient, some arbitrary number. And the differential of this function, y by the x, is equal to a cos of ax. So essentially what happens is that the multiplier a comes out the front here, as a multiplier, and then this sine function becomes a cosine function. And the thing within the sine function, well, it just stays the same. The thing inside the bracket stays the same. So let's look at an example. We have y equal to 4 sine 6x. So if we want to find the differential of y with respect to x, then we would have 4, because that's just a constant. This would be then multiplied by 6, because the 6 would come out the front. The sine would change to a cosine, and then the 6x just stays as 6x. So that means that we have 4 times the 6 gives us 24 cos of 6x. And that is our differential of 4 sine 6x. So what if we have a cosine function and we want to differentiate it? Well, if we have, say, y equal to cos of ax, then dy by x is actually equal to minus a sine ax. So essentially what happens is that, again, this multiplier a comes out the front as a multiplier, and the cos function changes to a negative sine function. So differentiating a sine function will give you a positive cosine, but differentiating a cosine will give you a negative sine. Okay, so just be careful with that. Again, the thing in the brackets doesn't change. So let's look at an example. We have y is equal to 5 cos 2x. So dy by x will be equal to 5 multiplied by minus 2 sine 2x. Okay, so the 2 comes out the front as a multiplier, and the cos goes to negative sine. So we can write that as minus 5 times 2 gives us 10 sine 2x. Okay, so that's our differential of 5 cos 2x. So we've now looked at differentiating some common functions. Now we're going to look at 3 really important rules for differentiation. So the first of these is the chain rule, the second is the product rule, and the third is the quotient rule. Okay, so let's start with the chain rule. So where would we use the chain rule? Well, we use the chain rule when we're trying to differentiate an expression where we have a function inside another function. So for example here we have y is equal to some function of u, and u is the internal function here, it's the function inside the other function, and u is in turn a function of x. So if we want to differentiate this entire expression, and we want to find dy by x, then the differential dy by x is equal to the differential of the external function multiplied by the differential of the internal function with respect to x. Okay, so to understand what I mean here, let's look at an example. So we have y is equal to 3x cubed plus 7 all to the power of 4. So we have this sort of external function, which is whatever is in the bracket to the power of 4, and then we have the internal function u inside the bracket, which is the x cubed plus 7. Okay, so our differential dy by the x is equal to, first we differentiate the external function, so the 4 comes down the front as a multiplier, thing inside the bracket just stays the same, we don't change that. And then the 4 becomes a 3 because we minus 1. That is then multiplied by the differential of u. So the differential of u is, with respect to x, we bring down the 3 to multiply it by 3, and we have 9x, and the 3 becomes 2. If we differentiate 7, it just goes to 0. So we now have, we can multiply the 4 by the 9, and we have 36 x squared, tidying this up a little bit, 3x cubed plus 7 to the power of 3. And that is our answer for that example. So to summarise, we differentiate the external function, keeping the thing inside the brackets the same, we don't change that, and then we multiply that by the differential of what's inside the brackets with respect to x. Okay, now let's look at the product rule. So where would we use the product rule? Well, we would use the product rule if we are trying to differentiate an expression that is made up of two separate functions of x that are being multiplied together. So here we have y is equal to some function of x u multiplied by another function of x v. Okay, so the differential of y with respect to x, y by x, would be equal to the first function u multiplied by the differential, the second function with respect to x, v by x, plus the second function v multiplied by the differential of the first function with respect to x, du by x. Okay, so again, to see what I mean, let's look at an example. Here we have y is equal to x to the power of 4 multiplied by cos x. So we can split this into two separate functions of x. First we have u is equal to x to the power of 4, and then v is equal to cos x. So the first thing that we want to do is find an expression for du by x. So we want to differentiate u with respect to x, so we can bring the 4 down as a multiplier, and then this becomes x to the power of 3. Next, we want to find the differential of v with respect to x. So hopefully you'll remember from a few slides ago, the differential of cos x is minus sin x. Okay, so now we can construct the differential of the entire expression. So we can say that the y by the x is equal to first u, which is x to the power of 4, multiplied by the differential of v, which is minus sin x. And to that we add the expression for v, which is cos x, multiplied by the differential of u with respect to x, which is 4x cubed. So we have now our expression for dy by dx, but we should really tidy this up into something that looks a bit better. So we can say we can take out x cubed from both expressions, and let's say we have then 4 cos x minus x sin x. Okay, so that is the product rule. Finally, let's look at the quotient rule. So we use the quotient rule when we're trying to differentiate an expression which is made up of one function of x divided by another function of x. So here we have y is equal to one function of x, u, divided by another function of x, v. So the differential of the entire expression, dy by dx, is now equal to the bottom expression, v, multiplied by the differential of the top expression, du by dx, minus the top expression, u, multiplied by the differential of the bottom expression, dv by dx, and then that is all divided through by the bottom expression squared, v squared. Okay, so to see what I mean, let's take a look at another example. We have y is equal to 2x divided by x squared plus 3. So we can say that for this example, u is equal to 2x and v is equal to x squared plus 3. So again, the first thing that we want to do is find the differentials of both of these with respect to x. So the differential of 2x is just 2. Okay, and the differential dv by dx, differential of x squared plus 3, so the 2 comes in front and we have 2x, and then the differential of 3 is just 0. Okay, so now we can begin to look at the differential of the entire expression, dy by dx. So that is now equal to the bottom expression v, which is x squared plus 3, multiplied by the differential of the top expression, du by dx, which is 2. From that we minus the top expression, which is 2x, multiplied by the differential of the bottom expression, dv by dx, which is also 2x. And then we divide that whole expression through by the bottom expression, x squared plus 3, all squared. Okay, so we want to tidy that up a little bit, so we can multiply out the brackets on the top, and what we end up with is 2x squared plus 6 minus 4x squared. The thing on the bottom just stays the same, x squared plus 3 all squared. So our final answer for this example is the 2x squared minus the 4x squared becomes minus 2x squared, so we can write 6 minus 2x squared. That's all divided through by x squared plus 3 all squared, and that is our final answer for that problem. So we have covered quite a lot in this video. We have covered differentiation of common functions like logs and exponentials and trig functions, and we've also covered the chain rule, product rule and quotient rule. So thank you very much for watching.